download are included in the presentation as well. This is slide 4. So you guys can follow along with us if you want. Otherwise, download the data yourself and follow along that way too. All right, Ileana, take it away.
All right, thanks, Lauren. So first of all, what is R? Simply put, it's a programming language and it's also a software environment. It's based off the S+ language. It's mostly used for statistical and data analysis. You can use it for graphing. And the main thing that makes R really useful is that it's free and it's also an open source software. So yeah. There's 2 types of R. So you have the standard format R, and this is just the most basic form. And here you can choose where each of your screen resides. We'll touch more on that later. And then the most preferred type of R is R Studio. This is a special version. And in here you have essentially one window and both screens are locked into a format and you can see them at all times. Again, this is just really preferred. It's more organized and it's easier to see and visualize everything. So here is an example of the R screen. On the right-hand side, you have your console, and this is where your code's going to be ran and your results are going to be produced. For the most part, try not to write your code here. It's whatever you type and run through there, it's not going to be edited and it can't be saved. So unless you're really confident in your R skills and you do type something in there, just hit enter to run that code. And then on the left-hand side, you're going to have your script. And this is, again, like the most preferred way to write your code. If you mess something up, you can just erase it, edit it out, and everything. Now, if you want to write your code here, what you're going to want to do is highlight the section and then hit either Control R. And if you have a Mac, I think it's Command Return. So Command Enter and make sure that it's highlighted. And then you could also just go to Edit on the window and then Run Line or Section. And so for R Studio, here on the upper left-hand corner, that's where your script is. That's where you're going to want to write, again, the most preferred line of code. You can make mistakes on there, it's okay. And then on the console, it's on your lower left-hand side. Again, it's advised that you don't write your code here. It's not editable, it's not savable. And to run your code here, you're just going to simply press enter. And for the script, you're going to highlight your code, and then right here, you can hit run, or you can also do Command Enter or Control R. So for the beginning use of R, we have your help function, and we're also going to show you how to install packages. Unfortunately, we're not going to be able to go over everything in R. So if you do have questions about R, it's really preferred that you go to r-project.org. You can find more information and things that you need on a more personal basis. And then you can also, into your script or console, type in help, close parentheses, and then within the parentheses, write whatever you need help with. And you can also put in the question mark, and that can also help you out. And to install a package, what you would want to do is type into your script, install .packages, and in the close parentheses, you're going to want to put in your preferred package. And then to activate the package, you're going to put in library, close parentheses, and then in the close parentheses, put in your desired package. And you can also, on the lower right-hand side of R Studio, you can go to the Packages tab and then hit Install, and it'll give you the option to install an R package. So now that I talked about installing packages, what are packages? So simply put, packages are extensions for R, and it essentially just improves the existing functions, or it adds to new functions that you have in R. So before you begin, you're gonna install your package in R just once, and then every time you open up R, you're gonna have to type in library and then the name of your package to call it, and you have to do this every single time. Some popular examples of packages in R include ggplot2, dplyr, that one's for data manipulation, and caret is typically reserved for machine learning. So really quickly, I'm just going to show you, this is how to install ggplot. ggplot2, I'm going to highlight, run. Oh, Okay, let's see. Okay, let's try this way. So just go into ggplot2. Let's install movies. So we're going to install this one. And you can see in your console, it's actually starting to install it, and it'll run everything through, and then you have it downloaded. And then let's try again, and let's do dplyr. There we go. So when we run this, you're going to see on the lower left-hand side in the console, it's going to start installing. And yeah. So if you wanted to activate dplyr, we would put library and then type in dplyr and then highlight run. And this is just going to activate it. So now you're ready to use dplyr. And if you have questions surrounding dplyr, what you could do is just put in help, close parentheses, and then you could put in dplyr. And then what should come up?
I think you misspelled dplyr.
Oh, sorry. Let's see. Yeah, there we go. So we can put help, highlight, run your code. And then here on your lower right-hand side, you're going to have essentially a lot of resources to help you out with whatever questions you may have. And then using the help function, we could also use a question mark. And if you have like questions like surrounding the mean, you could just run that. And then here on your lower right-hand side, you're going to be given more information and resources on things that have to deal with the mean and stuff like that. So yeah. So it's important to note that R is object-oriented. So R essentially creates objects and it also can manipulate them. So this can be vectors, an array of numbers, character strings, functions, or like more general structures that are built from such components. And during an R session, objects are created and stored by name. So simply put, everything in R is an object. And if you see here, the less than symbol followed by the minus sign is an assignment operator. So if you were to put X less than symbol minus and then space 5, R would interpret that as R or X gets the value 5. And then if you wanted to create a list in R, you would essentially do the name of what you would want to name your data, followed by the assignment operator, and then C close parentheses. And then in these close parentheses, you're going to want to put the values that are separated by a comma. And then from here, you can use your object in functions or formulas. So R comes with pre-installed functions, and they're pretty helpful. So if you wanted the summary statistics of your data, what you could do is just type in summary, close parentheses, and then the parentheses use the data set that you're going to want to use. And you could also list out the number of variables by using length, close parentheses. And then I think a really helpful tool would be the hash symbol to create like your own comments and things that won't be run, or like just like gentle reminders to yourself. Use the hash symbol, and it's really useful. R also has operations and things like that. So plus and minus, pretty straightforward. You can add or subtract. The asterisk for multiplication, / for division. The colon would be for a number sequence. It's interaction only. And then the upward arrow, I don't know what it's called, but for exponentials, you would essentially just use this symbol. So yeah, that would get you a squared. So for probability functions in R, if you wanted the probability or the density function, you would use P norm Q, where Q means quantile, and then you would enter your respective mean and standard deviation. For Q norm, you would use the probability, your desired probability, and then your mean and your standard deviation. For chi-squared distribution, for p chi-squared, you would use your quantile followed by your degrees of freedom and then your non-centrality parameters. For q chi-squared, you would include your probability followed by your degrees of freedom and your NCP. For F distribution, you would use PF, the data set that you're going to be using, your 2 degrees of freedom, and your NCP. And for QF, you would use your probability, your 2 degrees of freedom, and your non-centrality parameters. It's worth noting there are additional options, but we just included the most basic ones here, the main ones. And then to create informed data in R, to create a variable, you would title the data what you choose to call it. Here we're going to call it data, followed by the assignment operator, and then C, and then our chosen values. Here we have 1, 2, 3, 4, 5. If we wanted to combine a data set, what we would do is just use the same C, close parentheses, and then the chosen data that we're using. It's also worth noting R is case sensitive. So if you were going to put words into a data set, be sure to put quotation marks. And then to create a table, what you would do is use data.frame. And essentially that's just going to create a data frame. And then we can also use call names to label each column. So here we can do pre-copied. And then when you run the data, and then if you type in the name of the data of the table that we just created, you're going to get here on the lower right hand side or on the lower left hand side table that's created. And to extract a specific like point in the data or to extract a column, there's two methods to do it. You can do the listing method, which is essentially using the dollar symbol to call the variable that you want to use. So here we have table from the data set that we're choosing, and then the desired column that we want, GPA. And then if we run it, we just get the GPA that was mentioned earlier here in the second column. So this is the listing method. And then there's another way to do it called the metrics method. And this is essentially just naming the data, their desired data, and then using closed square brackets. What you would want to do is use a comma because we're not really picking a row yet. We're just picking a column. And then we want the second column, run that. And then this would yield the same result as mentioned before. Now to extract a row, we can't use the listing method. We can only use the metrics method. So here we would want to do, because we want the row, it would be 1 and then comma, because we just want the row, not the column. And then here we have the math major with the GPA. Now, if we wanted to extract like a specific point in the table, you would essentially just put it into, it's like coordinates. So if you wanted the second row with the first column, you would get it sociology. And you can see here we have second row, first column, sociology. And if we wanted another example, let's do third row, second column. And then here we would get the chemistry major with the GPA, and that's 3.65. So yeah, just be mindful that to extract a row and to extract a specific point, you would have to use the metrics method. And for extracting a particular column, you can use either the listing method or the metrics method. So yeah. So now I'm going to pass it over to Lauren, and she's going to be able to talk more about importing data and everything. Do you want me to stop sharing? Yeah, okay.
Yeah, thanks, Ileana. I'll go ahead and share my screen. If you guys wouldn't mind letting me know when you're able to see it. Oh, I think I'm doing the wrong screen. Sorry, guys. Classic. Okay. All right. Are you able to see my screen now? You should be seeing the slides.
Yeah, we can see it now.
Okay, yep. Perfect. So I'm going to be talking about importing data first. There's a couple of different ways that you can do it within R. Either you can actually write the code to import your data, which is sometimes a little bit extra, or you could just click the import data button within the tool itself. So if I go into R, I'll show you kind of both ways to do it. Here I have, remember Ileana mentioned using these hashtags here. This is the data, the code that I uploaded in that Google Drive there. So it's all the code that we referenced today, just in an R script, a saved R script. But if you want to read in data, you can either do it using read Excel, which is a package. And you can just use the read down square Excel function. And then here you put in your file path. Obviously, you're going to need to update this based off of your own kind of file path name for your computer, because this is my username at CSLRA. You're going to need to update yours based off of where you have the file saved. Alternatively, you can kind of cheat and just click on this import data set button here. If you're in RStudio, you can either select then where your data is coming from. So from text base, that means from like a CSV file. From Excel is anything that's like an XLS file, XLSX. Or you can update from any other kind of source here from SPSS, SAS, or Stata. I'm going to be uploading a file from Excel here. So if I click on this, what it's then going to ask me to do is find the file on my desktop. So you guys are going to see the whole host of messy desktop that I have here in just a second. What I'm looking for is my students.xls training document here. I'm going to click on that and then click open. It's then going to give me a little preview of the data here, and then also a little blurb of what the code would look like if I wanted to run this as code instead of as like a cheating kind of importing this way. I can also change the name of the data set down here. I could also then, instead of like, I have headers for my data set, so it actually has like the name of the variables, but I could also deselect this and it would just put the variable as a first row instead of the names of the data. I'm going to click on import down here in the upper right hand corner. We can see now that I have my object in the upper right hand corner for data. Remember, R is an object oriented data set, and you can always in the upper right hand corner see all of the items that you've created while you're walking through things. If you wanted to view the data, you can use the view function here, which is just view with a capital V and the name of the data that you want to view in the parentheses. We can just go ahead and run that. Just opens up that same thing here. So we can see my data set, it's 12 variables across, or excuse me, 12 observations across 4 variables. And this is just kind of an explainer of what I did here. If you wanted to import R code, so remember I showed you that R code, this training data set that I populated to the website there, the Google Drive. What you can do is click onto File and then Open File here, and then you just have to find the script wherever it is. I think it's this one. It's called training.r. If you just open that, it'll open up the script in a new tab at the top here. I already have it open, so it's not gonna do anything. Okay. Next, we're going to talk about graphics. So one of the really fun things about R is that it has a great graphics database. So you can either do so using base R or any one of the packages that R has. So I'll first show you how to plot using base R. This you really plot from the ground up. So it's kind of like a stepping stone methodology. Like you kind of layer in the parts of the graph. So if we just hop over to R here, you just kind of call the name of the function here. If I wanted to do a histogram, it's just the function is hist, and then my data set is students, and the variable that I want to call is age. So we use our $sign operand here to call the specific variable in the data set. And now we can see in the upper right or the lower left-hand corner of RStudio, the data set kind of populates. You can make it bigger or smaller just by kind of like dragging your windows around here. If you wanted to export the data set or like kind of copy the graph, you click on export here and then copy to clipboard. You can also save the image or save the PDF as well. There's also the ability, if I wanted to do just like a basic scatter plot, I could do so here as well. It's just the plot function. And now we're seeing the different students' GPA by student's age on the bottom here. So again, that's from our students data set here, just graphed in a scatter plot. So it's using base R here. We just did this one as well. If you wanted to use ggplot, this is a more complicated programming software that supports data visualization in R. So I know Ileana mentioned this earlier. It allows you to have greater ability to customize your coding compared to base R or other programming languages. The way that the code here kind of works, you always have to start with a call to ggplot. And then you specify in your AES, which stands for aesthetics, what your X variable is and then what your Y variable is. And then from there, you can add on additional layers like the type of graph. And these statements are all tied together using a plus sign. So for example, if I wanted to do a scatter plot, it would be plus geom downscore point. If I wanted to do column bar, column graph, it would be GM dunce for column, so on and so forth. You kind of get the drill, right? So for an example here, if we go back over to R, we have to first start by installing our package if we did not already. And remember, when you install packages, it has to be in quotation marks. So I already have ggplot installed, so I'm not going to go ahead and do that. But I will, every time you load R, you have to recall your packages. You always have to do the library function. So we can look down here in the console and just see that my ggplot is loaded, so I'm good to start using that data. And then if I run this code here, we can see, remember, I called to ggplot, and within my AES, I have my age, which is my X variable, and my GPA, which is my Y variable. And then I'm specifying also that I want to color the dots based off of the gender, which is another variable. I have to specify what my data is. My data is students. And then here I'm just qualifying, these are some, extra things that you can do within R. I'm saying that I want my dots to be larger, so they're gonna be size 3, and then I want my labels, my title, to be GPA by age and gender. So if I wanted to update my X axis, I could do that here as well, so on and so forth. There's a lot of different functionality within ggplot. You can see here I've updated the kind of graph. You can see I have my GPA by age. My little legend on the right-hand side here is telling me that my pink dots are for females and my blue dots are for males. So this is kind of a random scatter plot of GPA by age and gender. Okay, obviously a lot more functionality of graphing in R, keeping it high level for us today. Creating functions. So if you guys are working with a large data set, which you often are in data mining or like statistical analysis, there might be the option to do some additional kind of functions rather than manually coding items. So this is an if else statement. So here we have our test expression here. If, whether or not our value is true, it will either input the value or it will go ahead and do something else. So the general form is if, and then the statement. So for this example here, we are telling the data that if the data is greater than 0.5, label it as significant. And if it's smaller than that, label it as not significant. So if you go ahead and run that, our data is 0.2, 0.02. It's telling us that it's significant because it's less than 0.5. And then in this case, our data is now 5, so it's labeling it as not significant. You can also apply these into like columns of databases or columns of data. So if you wanted to like code a binary variable or categorical variable, you can do that within your data set using these if-else functions. There's also the ability to create for loops, and this is useful for repeating a specific block of code for a known number of times. A known number of times. So the example here is just saying for I, which is our integer or a number, for 1 and 3. So for 1 through 3, we're specifying how many times to repeat the code, print hello, and then print I times I. So whatever the number is, whatever the integer is in the values that we've specified. So let's go ahead and take a look at what this is. Our for loop right here. We're going to highlight this and then click run. So essentially what it did for I 1 through 3, it printed first hello, and then it printed 1 times 1 because that was the first value. Then it printed hello again, and it printed 2 times 2 because that's the second value. And then it printed hello again, and then 3 times 3, which is the third and final value that we specified in our little array here. That's what a for loop is. And again, this is what you would do if you know the number of times that this needs to be repeated. You can also run while loops, which is a counterpart to the for loops. And what this does is it's useful for repeating a specific block of code while a condition is being met. So in this example, it's while I is less than 6, print I, where I is equal to I plus 1. So we're only doing this while I is less than 6. If we go ahead and run this, we can see it's going to print whatever I plus 1 is. So 0, 1, 2, 3, 4 for our code here. A typo. If you go ahead and then into creating functions, sometimes the base functions that are available in R just won't be enough for you, and you might need to create your own functions. And the way you do this is using the function. So if we go ahead and click into R, the example that we're going to go through is how to create range. Hopefully everybody remembers what range is. It's just the maximum value versus the minimum value in the data set that you're looking at. So right now we're naming the function, which is just, the function of X. We can specify whatever in this function, we specify the number of kind of qualifiers that are needed in the functions. When you call the function, the number of things that you need to input in order for the function to properly run. So we're just saying in this instance, you only need an X. We're then saying what the calculation is, which is just taking the maximum value of X minus the minimum value of X. So this is the entirety of our function here. And if we run this now, we can see that we have a new function in the upper right-hand corner in our global environment here that's telling us we have a range, which is a function of X. From there, let's go ahead and create a data variable. So now we have an integer from 1 to 10. Our value of X is just a table or an integer. And then from there, let's go ahead and calculate what the range of X is. So you can see it's 9. It means it's working properly, right? If we wanted to also then just calculate like the range of a random set of numbers, we can do that as well. So like the array of 29 to 64, then our range would be 35. All right. Going then into statistical analysis. So Ileana mentioned earlier some descriptive statistics. There's a couple of ways that you can do this with NR. The first one is just by calling the individual statistics themselves. So for this example here, you can just call it the mean. Oh, I didn't create A. So I got an error here, mean A, object not found. It's because I didn't create A. You can see there's no object here named A. So we'll first create A. Now we have an A. You can just run individually the different kind of functions of A. Like, SD is the standard deviation. You could do the variance of A, so on and so forth. If we just run all of those individually, we get all the individual values. Otherwise, what you can do is just run the summary of A, and this gives you a whole host of different values. So kind of depending on what your need state is, if you want all of the available values or just the total availability. You can also calculate a confidence interval. So if you are looking to kind of see the confidence, if you want to be like 95% certain that your mean is within these two variables, this is kind of the formula that you would use here. If you know the standard deviation, then you would use a z-score with the known population standard deviation divided by your number of samples. Otherwise, you would use a t-score with the sample standard deviation instead of the popular standard deviation. But the x bar is whatever your kind of estimate is, and you always subtract to get the lower number, and then add to your standard or add to your value to get the upper bound. So for this example, we first have to calculate our mean. If we wanted to find the 95% confidence interval of whatever our mean is, we can calculate our mean of A first. And we're assigning it to the value. So now the object mean is equal to the mean of A. The standard deviation, SD, is just equal to the standard deviation of A. We're creating another object there. We can see we're adding them to the side here. And now we're going to create our lower confidence interval. So we have our mean. That's the value that we're trying to create the 95% confidence interval for. Our Q norm, which is the Z statistic of 95% there, times the standard deviation, which we just calculated. And then the same thing for upper, we're just adding instead of subtracting. So go ahead and run both of those. And now what we're going to do is just bind the two together. So we're just creating one kind of object where both of those confidence interval values live. If we go ahead and run that, we now have a new variable here called CI. And we always have to call it if we want to see what the actual values are. So you can see that the lower confidence interval down here at the bottom is negative 16.75. And then the upper is 79. We can also change if you wanted to see what the 90% confidence interval was instead of the 95. We can just go ahead and rerun this code. So you can see that it changes slightly. It gets a little bit larger. So That's how you would find a confidence interval. There's also a number of ways to do hypothesis testing within R. So if you're doing any sort of hypothesis testing, if you want to see whether or not the results of your survey or your experiment are meaningful, you can do a hypothesis test, which is essentially a way to see whether or not your results happen by chance. The general steps for hypothesis testing, you have to figure out what your null hypothesis is, which is the accepted fact. Then you move into state what your proposed new claim is. From there, you have to figure out the probability that you want to be certain your results are correct. That's generally 95%, but it could be 90 if you want to be a little bit less sure. And then you either accept or reject the null hypothesis based off of the results of your hypothesis testing. So there are a bunch of different types of hypothesis testing. The first being t-test. This is the most popular. You use this to compare two means when the standard deviation is unknown. The code is just t.test. There's also the f-test, which is commonly used to compare models that have been fitted against like raw data sets to see which model fits the data best. This is var.test. You also have to specify whether you want a two-sided or one-sided test, so whether it's greater, smaller than, or equal to. There's also the chi-square test, which is used typically for contingency tables and goodness of fits tests. The equation is chi-sq.test. You have to specify your x or your y if it's necessary. And then there's the Fish's exact test, which you use when your contingency table sample size is small and your row and column totals must be must be fixed. Yes, this is being recorded and this recording will be available. The call to that is Fisher.test. Finally, we have our analysis of variance or analysis of covariance, ANOVA or ANCOVA. This is used to compare difference in means across two or more independent groups. And the call to this is AOV, your X tilde, your Y, and then the data. Okay, for t-tests. There are a couple different types of t-tests, the first being one sample. So we still use the same kind of R code for all of them. It's t.test. If you wanted to use a one sample t-test, you just run the code as normal. You still have to specify whether it's one-sided, two-sided or less than or greater than. If you're doing two independent samples, you'd use the var.equal function here, and you set that equal to true to get a two independent samples if you want to see if the mean is the same across two independent samples. Or if you're doing a paired t-test, so like a pre and post test, that would be considered paired. You would use paired equals true. The additional paired equals true. All right, so let's get into an example. So we have two examples here. The first being we want to see if sleeping drug affects the sleep of two students. So this would be an example of a paired t-test because we're doing a pre and post of the same people. So our null hypothesis is that the mean sleep time is the same across the drugs for the two people. And our alternative hypothesis is that the mean sleep time is not the same across the drugs for the two people. So into our code here with hypothesis test, we're saying with our sleep data set, we're doing a t-test when sleep the extra equals group 1. So we're splitting our different groups into 1 and 2. And then we're saying paired equals true because it's a paired t-test. And if we go ahead and run this, sleep data set is one that's already embedded into R. There are a number of data sets that are already in R. So that's one that you don't have to like load any packages or anything. It's just included in base R. So if we go ahead and run that, we can see the results of our paired t-test down at the bottom here in our console. This is telling us our t statistic is negative 4.06. Our p-value is negative or 0.002. If our 95% confident, if we're trying to be 95% confident that our results are correct, our p-value has to be less than 0.5 for us to reject the null hypothesis. And rejecting the null hypothesis just means that the alternative hypothesis is true. So that means that we can say that the alternative hypothesis is true because our p-value is equal to negative 0.002. So that means that the mean sleep time is not the same across the two drugs for the two people. And if we wanted to do a t-test across two independent samples, so here we're using the Beaver1 data set that's embedded into R. Our null hypothesis is the mean temperature of the two beavers is the same versus the alternative that it's not the same. Again, we use the same t.test function as previously, except now we're using the alternative equals true as opposed to the paired equals false. And for these kind of operators here, you can either use F or a capital F or write out the entire word false if you're doing a true false statement. So we can go ahead and run this. Remember, Beaver 1, we're using the temperature variable that we're comparing. And we can see here that our p-value is less than 2.2 e to the negative 16th power. So it's very, very small, which means that we can reject our null hypothesis, or that the mean temperature is not the same across the two different types of beavers. All right, so remember I mentioned contingency tables previously. So here we're looking at whatever a contingency table is. It's just a frequency count for categorical variables. So here we can see between male and female, the favorite sport, 25% or 25 men said that football is their favorite sport as opposed to 87% of women. It's a quick high level overview. So a chi-squared test we would use for our contingency table if we wanted to see the proportions or probabilities match expectations. Here is the formula. It's chi-squared.test. The P is our vector of probabilities if it's not equal to the default. Here's our example. So for chi-square test, we have our contingency table on the right-hand side here, and we want to see whether or not there's a relationship between being given treatment and being cured from the disease. So we hop over into R here. We first have to create our matrix in R. So we're using the CS test. We're assigning it to be a matrix. Here are the values that we're importing, and then we're specifying that there's going to be 2 columns. So CS test so far just looks like this. It's a blank matrix with 2 rows, 4 values. We can then, if we wanted to add names to our CS test here, we can use the call to call names. And then we specify what our column names are. And because these are text, we're putting them in quotation marks. And then we can add our row names as well. So we're adding in the cured yes, cured no, treatment yes, treatment no. And if we want to take a look at what that looks like, now we can see we have our same kind of values, but now we're adding in the different rows. We then have to specify that it's a table in order for the table to work in the chi-square test function. And then what we did is we added margins. We just added in the totals here. So we can see the total sums for the add margins to our, and then our call to the table. From there, we can add the chi-square.test function. And the only thing we need to do is just put in our table and it'll run the data for us. So again, we're trying to see whether or not the proportions are the same or the portions are the same across the contingency table. Our p-value is very, very small again. So we will reject the null hypothesis. We can see that the variables are not independent or that they are dependent. Here's the same code that we just went through. Fisher's exact test. So you would use this if your row and column totals are fixed. That's the main reason. Alternatively, if your sample size is small. So this exam, we wanted to see if there's any relationship between studying and passing the exam. If, for example, only a certain number of students can pass the exam, if that number of students who can pass is fixed. So we're trying to see whether or not the variables are independent. So for this example, we have to go through kind of the same example of building our matrix here. So we're using the matrix function, our contingency table. Here are the numbers that we put in, and then we have the number of columns. So if you just want to look quickly at what that does, we have now our kind of naked matrix here. It needs its column and row names, right? So we're using the same column names function, the matrix that we want to add the column names to, and then in a vector here, the names. And then if we call fish test, that's the name of the matrix. If we call it again, we can see what it looks like. Here's what it looks like. So it matches what we had in our presentation, right? We can then go ahead and add our margins, add our totals, make it a table so the function recognizes it as .table, just to convert an object into a table instead of an integer. So now it's recognizing that fish test is a table in the upper right-hand corner. And then we can run Fisher.test, and we just need to put the name of the contingency table in when we set it up like this. And here we can see that our p-value is super, super small, 0.008. So we reject our null hypothesis. There's evidence of a relationship between studying and passing the exam. Here's the same thing, just in R code. Do we have any questions as I'm going through this? Okay, if no questions, I'll continue. Next would be an F-test. You would use this if you're trying to compare two variances. Here's the function var.test. Oftentimes, though, this is used in something like an analysis of variance or an ANOVA. So the difference between ANOVA and ANCOVA is ANOVA, you use it to compare the difference between the means of two or more independent groups, so categorical variables. You would use an ANCOVA if you're trying to use control for the effect of a continuous variable. So I think ANCOVA with the C for continuous. The function is AOV. So let's go ahead and look at the R code. So we're using the chick weights data set here in R. If we wanted to see just like the kind of first couple of rows of the chick weights data set, what we can just do is do head and then chick weights, and it'll just print the couple of, first couple rows here of the chick weights data. If we wanted to just spend some time looking at our data set, we can also do name and then the name of the data set. And what that would do is just return the names of the different columns that we have. If we wanted to view the chick weights data set, we do view with a capital W and then do chick weights. We can run that and it'll open it up in a new tab here. So we can see the number of observations. If we wanted to do the length too, we could do that. So just LEN. We can see, it's only 2 because it's telling us the number of columns. Whenever we do kind of a formula within R, we use this tilde sign. So we always name our Y variable first, our independent variable, and then our X variable second, and we do this tilde here in between the two of them. And then we have to specify always what our data is. So we're saying we want to figure out whether or not the different types of feed for the chicks, we can see, if we look back at our database, the different kind of feeds here that we have, whether or not that impacts the weight of the chicks that we have on the left-hand side here. So if we go ahead and kind of run this, you can see that we have a new data here. It's a new model. So we have assigned our model, but now we also have to view the results, right? So to do that, we use the summary function, summary, and then the model that we save the results to. And here we have our results. So the way to view this is to see the feed is our X variable here. Obviously, this is kind of the results of that. We have the F value, the F statistic, and then the probability that this variable is significant here. Our significant codes are listed down below, but we can see it has 3 asterisks, which means that we can be very confident that our results are significant. So that's an analysis of variance AOV. If we wanted to get more information on the analysis of variance function, we can always do the question mark AOV, and it'll pull it up in the kind of right-hand corner here. So that's always helpful. Alternatively, we could do like help AOV, I believe, as well, and it'll show us kind of the same exact thing. So they're kind of synonymous when it comes to functions. Any questions on analysis of variance? This is kind of the same thing, but essentially what we're trying to test here is that there's no difference in mean among the different types of chicks weight, different types of weights for chicks by the different types of feed. With this bar stem and leaf plot is just showing the different type of mean weights across the different types of feed. So obviously we could see that at least one of the means was different based off of this kind of wild graph here, right? They all look all over the place. All right. Our next section is modeling. Again, pretty complicated stuff here in regression analysis. So whenever you're running a regression analysis, you're trying to figure out whether or not there's a relationship between 2 or more variables. So you could be trying to predict something, You know, if you want to predict like house prices based off of, you know, the number of bathrooms and the square footage, that would be something that you could use linear regression for. So our dependent variable, or the y variable, is the variable that you're trying to understand or predict, which is here in our function. And then the independent variable are the factors you think have an impact on your dependent variable. So we have our intercept for a population, that's our beta 0. If you remember the y equals mx plus b, this would be our b, beta naught. Our independent or dependent variables are y. And then we have our slope here, which is beta 1, aka our mxm. And then our independent variable. And we can have any number of these. We can have I number of these. They would all have their own beta coefficient. And then also our random error term, because we're never going to fit our data 100%. So the error is always going to be there as well. There are a couple different ways that we can kind of determine fit of our model. The first one is R squared. This is also known as the coefficient of determination. And this measures how close our data is to the fitted regression line. So if we have a regression or a coefficient of determination of 80%, that means that 80% of our variance in our y variable can be explained by our x's. So that measures the proportion of variation in the dependent variable that can be explained by the independent variable. We want a high coefficient of determination. We can also do an F-test of overall significance, which is just testing to see whether our null hypothesis that we're trying to disprove is that the model with no independent variables fits the data as well as the model that you've created. So essentially, does an empty model fit the data better than your model does, which is what you're trying to disprove. So there are two kind of ways that you can determine whether or not your model fits the data well, very basic, high level. There are a couple different types of regression models, and this just depends on kind of the data that you're trying to fit. So a linear model, if your data is distributed normally, you use the function LM. Again, we use our little tilde here to fit the data. So our y and then the tilde x, you always have to call to whatever your data is as well. So this is just for any old linear modeling. So example, predicting temperature, your house price, anything like that would be a linear model. You could also do the GLM function, which just stands for general linear model. And then the family would be the identity link here. And whenever you create you always want to store an object whenever you run a model like this, and then run the summary function on it. So you're creating an object for your model results, and then you're viewing the summary after the fact. Because remember, R always views things as objects. You can also run a logistic model. This is when you're trying to predict a binary y variable, so a 0, 1 y variable. So if you're trying to predict whether or not somebody's going to die of a heart attack, you know, the 1 signifying death, you can do that there. Whether or not it will rain outside, that's a 0, 1 variable. That's what we mean by binary. There's only one option. The function here would be GLM. And then you would do the family equals binomial link equals logit in order to get it to run for a binary variable. Again, we still have the same tilde function here. And then finally, Poisson model, if you're modeling count data. So if you want to predict the number of customers that will come through your store, or the number of cars that'll be in traffic, that will be count data. Again, you use the GLM function, so the same one for logistic model, and then you do the family equals Poisson and link equals log. And again, for each one of these, and including the analysis of variance, it's similar. You always want to run the kind of save the code, save the model to a specific object, and then do the summary function to view the results of it. So let's look at our example. So here we're using the MT cars data set. If you wanted to view, this is a data set that's pre-built into R here. We have our different cars on the left-hand side. That's our kind of, you know, our rows. And then we have the miles per gallon, a whole bunch of different, you know, car-related metrics. Wanted to see the names of the variables, we can do the head function, cars, and it'll just show us kind of the first couple rows of data. You could also do a summary of the MT cars data set. And what this just does is it gives us, for each one of our variables, the minimum, so on and so forth from there. the mean value, so on and so forth. For this example, we're going to try and predict miles per gallon. So we have our model. We're going to first store the value to model, store our model to the value model, and then we do our tilde. So our y variable, the one that we're trying to predict, our miles per gallon, we do tilde. And then here I just have a period because I want all of the other x values to be included. But if I know, I'm just going to try and predict, model 2. I'm going to do a different one, lm tilde, and we can just list out our y variables, maybe cyclical plus disp data equals empty cars. So we'll run this first one, which is fully fit with all of our data set, and then we'll run the second one, model 2. We wanted to see the, remember, we have to then view the summary of our model. If we go ahead and click on that, now we can see the summary of all of the data sets. So here we're seeing all of our independent or all of our dependent variables, the estimate of the variable, and then the individual significance levels of each individual variable. If we look down here at the bottom, we can see our coefficient of determination, or our R squared, which is 0.869, which is telling us that 86.9% of our variation in our Y variable is explained by our X's. We can also then see our p-value, which is that f-test for the f-test. If we remember that, the overall significance, which is testing whether or not a model with no independent variables fits the data as well as your model. So if it's small, that means that your data is fitting, or your model is fitting the data better than nothing at all, which is good. We can also then see the summary of the model with only a couple of coefficients, and now we can see the without as many variables, our variables are now more significant as well. Our R squared, however, is less significant, so we're explaining less of the variation. So we're only explaining 74.3% versus the 80.66. Something that's really helpful too, if you want to run an old line of code, just a tip, you can just click the up button and it'll like kind of show you all the things that you've run previously. You can use the up and down buttons to kind of toggle through things. This is just our code for that. So we have a lot of time left. I don't know if anybody has any questions or anything that they want to run through specifically within R. The next thing that I was just going to talk about was some helpful links and cheat sheets. So this first one is just the link to rstudio.com, which gives you some like helpful documents about how to, plot things in ggplot or something, so on and so forth. So data camp, which is very helpful. In terms of why you would want to use R, it's a very effective tool at data handling and storage. It's really good for graphing. That's the main thing with R, is it's really good for graphing as opposed to other languages. It's open sourced, so it's free. You can right now go ahead and download RStudio and just kind of start working on R. It's also relatively simple programming as compared to other coding languages.
Yeah, great job, Lauren and Ileana.